let's talk about how do we find the eigenvalues and eigenvectors of a 2 by 2 matrix. Here is the idea. We have a 2 by 2 matrix, A, and imagine if we multiply by a 2 by 1 factor, we'll call it V. If this is equal to a constant multiple, and we'll call that constant lambda, which is going to be the eigenvalue, and lambda is written like this, it's a Greek letter. If we have this is equal to a constant multiple times the same factor, then this right here is a eigenvalue of the matrix, and this right here is the corresponding eigenvector. Now, in order to achieve this, we can move this to the other side and factor out the V. So you can see that we will get A minus lambda, but this is a 2 by 2 matrix. When we factor out this thing here, this has to be a matrix as well. Well, when we factor it out, remember just multiply by the identity matrix. Here we have a 2 by 2 case, so this will be a 2 by 2 identity matrix. And then multiply by the factor V, we need that to be 0. Technically the 0 factor. And then right here, in order for us to achieve this, the key is we can apply the determinant. And we just want to make this part right here. The key is we want the determinant of this thing, A minus lambda times I, we want this to be 0. So this is what we have to do. And keep in mind, lambda can be real or complex. If lambda is real, the idea is that when you have this eigenvector multiply with this matrix, the result is just going to be a real number times this factor. So it's just you scale the factor bigger or smaller by this factor. And in fact, if lambda is complex, it's going to be a rotation thing, but we can talk about later on. Let's go ahead and finish this real quick. So we will need the determinant of, for this thing, all we have to do is go to the diagonal and then subtract lambda from it, and then keep the rest. So 1, 2, and we want this to be 0. Now, for this determinant, we do this times that, and then minus this times that, which is just 2. All right, multiply it out, so that's 12, and then minus 4 lambda, minus 3 lambda, plus lambda squared, minus 2 is equal to 0. And we have lambda squared, minus 7 lambda, and plus 10, that's equal to 0. Factor it, lambda minus 5, lambda minus 2, we get 0, meaning lambda equals 5, or the other one, lambda equals 2. So I guess we can see that we have two eigenvalues. We call this lambda 1 and lambda 2. And now, how do we find the corresponding eigenvectors? Here's the idea. Firstly, we want to find the vector v, and it has two components. We'll just call it x, y. So let's start with this right here. Let v equal x, y. And then we have two lambdas, right? Let's look at the first one when lambda is equal to 5. Plug into here. Then you see we want to have A minus 5 times the identity matrix times v is equal to 0. So we just have to go to the diagonal and then subtract 5. So we have 4 minus 5, and then 1, and then 3 minus 5, and then 2. And then times our vector x, y, and we want this to be the 0 factor, like this. And of course, you can work that out real quick. This is going to be negative 1, 2, 1, negative 2, and x, y, that's 0, 0. And you can see if you multiply this out, you get negative x plus y. We want this to be 0, and then the other one, 2x minus 2y, we also want this to be 0. And if you look at this real quick, you see that this has infinitely many solutions, because if you multiply the top by 2 and then add it up, you get 0 over 0. So this is consistent. So what you want to do is, if you look at the first equation, you can see that adding x to both sides, y is the same as x. So just pick whatever you want. You can go ahead and say let x equal 1. Then y will be 1 as well. And that's pretty much it. So when lambda is equal to 5, the corresponding eigenvector is just 1, 1. Okay, and then let's do another one. When lambda 2, which is equal to 2. And then do the same thing. So plugging 2 into the diagonal by subtract, it was right here. So it's 4 minus 2, 1, 2, 3, minus 2, and then multiply by xy. Okay, so it's 2, 1, 2, negative 1. No, 2, 1, 2, 1. And then xy. And you see that's 2x plus y equals 0. Of course, it's the same equation, so you don't have to write it down again. And right here, you can see that y is equal to negative 2x. And I can say, let x equal 1, then correspondingly, y would be negative 2. So when lambda is equal to 2, our corresponding eigenvector is equal to 1, negative 2. That's it. So here's the bonus part. Earlier, we got the eigenvalues of our matrix. In fact, there's a quick way to check to see if we make a mistake or not. Here's how it goes. The idea is that if you do the trace of a matrix, this right here will always be equal to the sum of its eigenvalues. This is always true, regardless if the eigenvalues are complex or real. So how do we do the trace? You just look back to the original and then just look at the diagonal entries and just add them up. So this is 4 plus 3. And we get 7. What were the eigenvalues that we got? 5 and 2. So is this equal to 5 plus 2? Yes, indeed it is. Yeah, so this is the quick check. But earlier, if somehow you solve the equation, you end up with 1 and 6, and then you say, hey, 7 is equal to 1 plus 6. Well, that is still wrong. It's just like, I don't know what to say.